In this video, we're going to take a look at the concept of polyprotic acids. So many of the acids that we've studied are monoprotic, mono meaning one, protic meaning proton. So essentially, it's an acid that is able to ionize and donate one hydrogen specifically. So HClO is a monoprotic acid because it only has one H atom or ion to donate. HCl is a monoprotic acid because it only has one H to donate as well. Even ethanoic acid is considered monoprotic. And this is a really important one to highlight because you'll notice that there's many H's here, but they're not all acidic H's. They won't all be donated. Only this one will be. And there's reasons for that we can discuss in a future video, but the main idea is that for H to be donated, it must not be strongly attached here. It is still a covalent bond, but what happens is you have a lot of electron withdrawing power because this is so electronegative here. We're pulling away electrons from this area, and so in theory this area is becoming quite partially positive, and so a base or anything with extra electrons kind of pick up that H pretty easily. So in our situation here, water with lone pairs on the O is able to take away this H, and so the H goes here. But the main point is that it's only one H being donated, so even ethanoic, having many H's, it only has one H to donate. That makes it monoprotic. So it's a monoprotic acid as well. Now there are some acids that are called polyprotic, meaning they can donate more than one H. So H2SO4 can donate two H's, so we would call it diprotic. H3PO4 could donate three H's, so we'd call it triprotic. We oftentimes just call them polyprotic, but you could specify to that degree as well. Suppose that you wanted to determine the pH of a solution of H3PO4. Well, if you think about it, you would have three ionizations. H3PO4AQ plus water produces H2PO4. That's the first ionization. 2 minus AQ plus H3O plus AQ. So you need to figure out this H3O plus here using an ice table. But then don't forget this also ionizes. So this would be H2PO4. By the way, don't quit the video and give up just yet. You're going to like the ending here, so just pay attention. H2PO4 plus H2O, liquid, equilibrium. We're going to get HPO4. Oops, and I shouldn't have said 2 minus here. I don't know why I did that. This should be H2PO4 minus. Here, and let's change that here too. See, sometimes you notice mistakes as you're writing the other steps. Here we're going to have HPO4 2 minus now, AQ, because this loses another H, plus H3O plus. So we'd have to know this H3O plus as well, so we'd have to figure this out using an ice table and the Ka for this. But then don't forget, this also ionizes. So you'd have to figure out, okay, so HPO4 2 minus AQ plus water, reversible reaction, PO4 3 minus because you lose another H, plus H3O plus. So now you have another source of H3O plus here that you'd have to figure out using the Ka of this, and you have to find X basically 3 times. So it's like you're making 3 ice tables. If it was that difficult, no one would want to do these problems. It's actually much easier than this. Let's analyze the Kas of phosphoric acid and its conjugate bases. So if you look at the Ka1, it's 7.1 times 10 to the negative 3. And then Ka2 is 6.3 times 10 to the negative 8, and then negative 13. So these Ka values, the Ka2 and Ka3, so this would be Ka2 here, this would be Ka3, and then this is Ka1. Ka2 and Ka3, they're both significantly smaller than Ka1. They're so small, this H3O plus here and this H3O plus here is basically insignificant compared to the H3O plus resulting from the first ionization. So when you have a diprotic or triprotic acid or polyprotic acid, all you have to do is make an ice table for the first ionization. You can ignore the other ionizations because they're so small compared to the first that they're going to contribute very little to that pH. So you essentially don't have to worry about these ones, and you just have to do this first equation here to find the H3O plus. While yes, there might be some more added from here, again, it's very insignificant. It wouldn't really change your pH answer in the end. So you just have to do it one time. If you do see that, just remember that for the polyprotic acid, you just need to do it once. There is an exception for that though. H2SO4, when it has a concentration less than 1.0, you would actually have to use both Ka values, but we're not really going to explore that. If you are interested in exploring that and seeing why, you're more than welcome to see here and also try a problem there. Try this practice problem here before the end of the video. So pause it, try it out. So oxalic acid, H2C2O4, is it monoprotic or polyprotic? And then write out the ionization equations and expressions for oxalic acid. So pause the video, try it out. So you'll see here that we have essentially a dicarboxylic acid. You have an H here to donate and an H there to donate as well. So it looks like we have a polyprotic acid. And because we have a polyprotic acid, we're going to have two ionizations that we can write out. We don't need to calculate both, but we can write out both Ka expressions, or ionizations, and then associate them with their Kas. So we'll start off with the first ionization. We're going to do H2C2O4AQ plus H2O liquid. It is a weak acid because it's not one of our strong, and you can see here it's a pretty small Ka. We're going to get H, so our first one donated, C2O4 minus AQ plus H3O plus AQ, and this would correspond to Ka1, which is the only one you need to calculate to find pH if you were asked that. But then this one here could ionize as well, and so you'd have HC2O4 minus AQ plus H2O liquid, reversible reaction, C2O4 2 minus AQ plus H3O plus AQ. And this will correspond to the Ka2, which is smaller than the Ka1, so you wouldn't really use it in your calculation to figure out the concentration of H3O plus. And so that was an example of writing a Ka1, Ka2 ionization expression for a polyprotic acid. And again, we knew this was polyprotic because there are two H's that could be donated, because you essentially have carboxylic acids here and here.